Okay, so this is part 2 in this series on building this guitar preamp. Here's a little chart I showed you before. So we're right here, and in the circuit we are down here. This is more or less the distorted part of the circuit, and let's just kind of zoom in on that for now. Okay. Well, let's see here. Let me clean this up a little bit. Okay. So, at first this looks kind of complicated. I mean, I suppose it is. But I'm just going to kind of walk you through how this works and sort of how I came up with it. So I'm going to start with like a simpler circuit beforehand, and we'll kind of build out from that. Now, really the main part of this circuit is, I would say, right here, this area right here. And this is basically an amplifier that's coupled to an emitter follower and has a feedback soft clipping mechanism. So let's kind of look at that a little more. Okay, so just kind of built this circuit, but you can see here, I sort of mentioned this is the central, I don't know, the central part of this distortion circuit, at least in my mind. And that's how I actually built it. I built something like that, and I kind of built around it. And here's an example of like a similar circuit. Let me see if I can get this a little closer and zoom in a little bit better. Okay. So this is just kind of a sample of a soft clipping circuit. See if I can kind of zoom in on both those somewhat. Alright, that's not bad. Whoops. Okay, anyways, let's just look at this circuit for a minute. It's, you can see up here, this is basically an amplifier circuit. You've got some biasing here, and you've got 10K here and 10K here, which normally that would be like a gain of 1, but we've bypassed this lower capacitor, this lower resistor, put it on like a full bypass, just capacitor to ground, and that just really makes this run at full gain. And of course, this is an inverting amplifier, so it sends the signal here is going to be inverted from this signal. Now, if you notice here, I put 1.8K series resistance, because up here that's the output impedance of what's feeding into this. So this is kind of similar. So let's run this for a second. First of all, I'm just going to take this feedback mechanism out of it for a second and run this. So this is just kind of a full-blown gain that's as much gain as this circuit will put out. Let's see, I've got the voltage is varying. It's the input voltage increasing. Here's the output voltage. Okay, so you can see this is let's just focus on the output voltage for a minute. It's biased here right at 6.3 volts. This circuit, this circuit here, it's like I said, it's biased so that the amplifier is around 2/3 of the voltage, and this should be biased around this area here, like 1/3 of the voltage. It's just kind of a generic amplifier. As an aside, if you go to, and I would recommend it if you haven't, read through Bipolar Junction Transistor Cookbook in Nuts and Bolts. It's an awesome read. It talks about all these sort of standard circuits. But so this is kind of what you get here. This is just an amplifier that's maxed out in clipping. So we're going to feed that back to the base here. Okay, so let's close out of this. We'll hook this up and we'll see this. Now again, this is a kind of a standard soft clipping type circuit. So here goes that input again. Got to wait for this to run through all those voltages. Before I click on here, you'll notice something here. We're running this from 0 to 700 millivolts, but it's only going up to 450, and this is the input. Why is that? Well, it's because this has 1.8 K of input impedance. You don't see it there. It's part of the source here, and it's going into something that's probably like 5K or so. At first glance, you might think it's higher than that, but this bypass capacitor just leaves the I guess the lowest parallel input impedance is the base. Maybe that's worded a little bit funny, but when you look at the input impedance here, we'll probably not get into this a lot, but basically a bypass transistor like this, it doesn't have a whole lot of input impedance. So let's take a look at the output now. Okay, now here's some output here. Let's zoom in on this. So you can see this is kind of clipping. It's kind of a soft clipping. Here it kind of starts to peek through. Let me zoom out again. And you know, at first this may not seem obvious, but when you feed this back here, you know, it's being fed back from sort of a source that has 10K input impedance going this way, and it's kind of competing with a signal coming in this way of opposite phase with lower input impedance. And these input impedance, actually the mismatch between this source and this actually kind of do matter. And let me demonstrate that for a minute. Okay, to demonstrate that, let's close this out, and here we will change this 1.8K down to, I don't know, 10 or something, or we'll just take it out altogether. So now we have a super low impedance source coming through here. Let's see what we get when we run it. Okay, it's running. Well, the first thing you'll notice, it goes up to full 700 millivolts because, you know, it's a super low impedance source going into 5K or so. Let's see here. Okay, and you can see it's sort of really, you know, these different feedbacks that are sort of competing for the base signal here. You know, it's a complex interaction because you've got you know, the source being amplified, but on the other hand, it's a much higher input impedance and it's opposite phase, and so you just kind of get this, you know, peaking a lot worse. Now, you know, 0.7 amplitude is not a super high amplitude for a circuit like this, so let's just kind of make this, I don't know, let's make it go to like say 2.5 volts or something like that. And I'm going to cut this just so we don't have to wait for the computations. I'm going to do it in 0.25 volt intervals. And let's kind of see what we get here. Okay, so it ran through. Let's take a look at the input. Again, it's going up to 2.5 volts. Look at the output. See, it's really peaking through there. It basically sort of this whole concept of the feedback, limiting it and clipping it, sort of breaks down at these high voltages. You know, when this source impedance on the feedback mechanism itself is much higher than the input, and so you know, this voltage can clip right across here too, going straight from more or less the input. Well, not technically this is the input, but right here going across either way, and that's why you get this signal. It just kind of doesn't work anymore. That happens if you have low, I guess very low input impedance here, and you're really driving the circuit hard. So this is sort of a circuit that has some limitations. There's actually a circuit similar to this. It's by Joe Davison called Easy Drive, and I would share it with you, but I think it's copyrighted from what I can tell, so I don't really want to put it on here, but I would really look at that, and that is probably, to me, the best single transistor distortion. But what you don't really see necessarily in that distortion is it depends on some input impedance coming from the guitar, and also if you drive it too hard it totally breaks down. But fortunately your guitar does have some input impedance in it, and also it only gets so loud it doesn't get up to super high voltages usually. So saying that, this kind of circuit can be very good in the sort of phonic or the telephonic properties of it, I think, just sound good, but with one transistor you can't really get where you need to if you need higher gains. So I'll show you how I address that. So before we do anything else, let me put this back to 1.8K, which is kind of what we were working with, and let me bring this up. Here's something. I'll kind of put them side by side so you can hopefully see here. Okay. Let's see here. Okay, so this circuit is very similar. And see, what I did here was I took an extra transistor and I hooked it up directly, DC coupled this transistor and made an emitter follower basically right off the let me show you this, right off of the amplifier. So basically what the emitter follower is, you can just hook up another transistor right to here. It basically copies the signal, brings it down to 0.7 volts less or so, and it lowers the input impedance of it. So these are wonderful. I'm always tacking on just two extra components here all the time, because it's just such an easy cheat to make your amplifier low impedance. And the equation is basically you take the HFE, which is say like 200 or 300 here, and you multiply it by the resist. I apologize. I just had a mental breakdown for a minute. But what you do here, I was thinking incorrectly for a second. The output impedance of this circuit is like 10K, and to find out the output impedance here is you divide by the HFE here. And let's say the HFE of the transistor is like 250 or something like that. You'd have like 10,000 divided by 250 is about 40. So it's pretty low impedance, especially compared to these other impedances that we're mixing in with. So that sort of addresses this issue, and let's take a look at this. Now we've still left, let's make sure we've got apples to apples here. Okay, so we've got resistance of 1.8K on the sources. Both sources are the same. We've got this going up to 2.5 volts. Let's see how this does. Okay, so like we already looked at this. I mean, it clips like crazy. I mean, this isn't really usable. Let's check this circuit out now. And you can just kind of zoom in here. You can see it works fine. In fact, if you have experience with distortion circuits, you can kind of see this is probably going to sound pretty good just by, looking at them. Let's just kind of look here. Okay, so this solves the problem of being able to drive this circuit. And that's the thing, like you could use this circuit here, with lower voltages and then re-amplify it and do whatever you want. But you can only present to this circuit a certain amount of voltage before it just breaks down. So this, coupling it this way through this feedback mechanism, it allows you to drive this harder. Okay, and if you look here, the harder you drive it, the less symmetric it gets. And another thing you can play around with is this feedback capacitor, because if you lower it, then not all of the high frequency signals get through as well. And let's take a look at that just for fun. Let's see, we'll break this. Here we go. Oh, let's just put 1. Let's go with 0.47. We'll just kind of really bring it down on almost an order of 10 magnitude. And all right, let's see what we got here. So you can see it's sort of again, you can listen to this stuff by ear. You can see it's peaking up higher. I mean, it's still symmetric and usable, but it is higher because it's not, not as much signal is being fed back. And remember, this is an opposite phase. When you hop on one of these emitter followers to an amp like that, it just lowers the signal. It doesn't invert it. It's non-inverting. So it, feeds back here, but doesn't fully feed back and stop it. And I think if we put a bigger one on, we'll see that some of that asymmetry is gone. Zoom in a little bit more here. So we're gonna, let's just put like, I don't know, 100. So let's see what we got there. Okay, so this is with a lot of feedback coming through. Let's see, take a look at that signal. Okay, you can tell it's just fully clipped. So by giving like a partial feedback, it ends up giving it some asymmetry. And that sort of helps, I think. Now, I've used bigger feedback capacitors there, and sometimes it's subtle. It's definitely subtle. This might even be a little bit. Let me run that through. This might even be a little bit too much. Like I might like to maybe use like a 2.2 microfarad capacitor, but whatever. You get the point. Is you get a little bit of soft asymmetry that comes through here. And so far, like this, I haven't really tested this out by ear just this on its own. Of course, you have to buffer it before you go in anyways from a guitar. But then once you buffer it, you need to insert a 1.8K resistor or so. So there's a lot going on here, but you can see the basic structure of how this works. So to recap so far, the main thing I discovered were soft feedback mechanisms like the Joe Davison circuit is wonderful. They have a good sound to them, but I wanted to be able to drive one harder and take advantage of that sound by just sort of really sticking bigger signals into it and doing so and driving it hard as a different stage. So this is kind of the center of it. And then I'm going to show you that I drove it harder, and I'll show you other modifications I made to this. So let's just kind of go back up to this. Now hopefully this will start to look kind of familiar. You've got that amp here. You've got gain here. Now this I didn't fully bypass it here. I've got a 100 ohm resistor on a pot that goes up and down, which acts like a gain control. You've got that transistor with the feedback mechanism. We don't have to talk about this too much, but this is you're supposed to do this with high gain amps and really any type of amp to filter out any noise that might be coming back through and making it to the bass and re-amplifying. That causes bad oscillations, noise, and so forth. So okay, so we won't really focus on that too much. So what is this? This is just I guess we can look at this part next. This is fairly straightforward. Kind of zoom in on that. This is just an amp. I mean, you've got you've got your biasing resistors. You've got sort of an overdrive circuit here. Instead of putting a pot here, I just used a switch to sort of bypass this and give it some more gain. And then you can see there's that 1.8K resistor. Now, I don't know that these are actually the best per se. Looking at it overall, it does work. I mean, of course, I've tested it. And I think the way I probably came up with this gain stage is I kind of set this down maybe near 0.8 volts or so, because I think I looked at some older amps and they were kind of biased with the input being lower, giving more room up here for the amplification. I don't know that that's necessarily the best in hindsight, but it sounds good, and so I didn't want to mess with it, and I didn't think it was worth messing with. Especially, I think if it clips, it's still going to be. I think when it's fed to the next circuit, that clipping kind of gets, I believe it gets omitted because this clips it less than this does, less than the input would clip at. So I'm not even sure if you totally can hear it too much. At any rate, I didn't want to mess with it because I just kind of put this together quickly and it sounded fine. So I left it, basically. In hindsight, maybe there is something better driving mechanism to go into this. You're still going to need some resistance there. You can't make it too low. But that's basically the circuit. You've got a driving circuit, and then you've got this soft clipping circuit that has this extra transistor to help the feedback mechanism work better, and then you've got a partial feedback coming through instead of just totally feeding back. And that's kind of right here. This is not too bad sounding. But what I did after that is, a lot of these circuits, they have too much mid-range. Like if you ever just made like a Boss DS1 distortion or something like that and listened to it, I mean, it's got so much mid-range in it that to me it's like just, it needs EQ'd so much before you can use it. So I sort of did that here, and I also did some other things we'll talk about. So this next stage is just this is a bridge T filter actually, and I put a little switch on it, so when the switch comes down, the bridge T filter is totally on, and when you put this together, when you disconnect it, it throws a resistor in there and sort of pushes this mid-range signal up a little bit. And I have it so that it's similar to a lot of vintage designs, let's say, when this is instituted. And it without talking to it too much, I mean, I just work with filters a lot, and this ended up being what I went with at the end. Also before when I did it, I think when you sort of turn this on, and there's a big mid-range cut, I think you could turn the mid up here and then turn off the mid-range cut and turn the mids down. I think I had like the levels matching, but I ended up redoing this, so I'm not sure if that's as relevant. Sorry to ramble on about that, but I did put some thought into this, and actually I think to me it's kind of interesting how I came up with this. I'll just briefly talk about that. Just this is kind of interesting. I guess maybe I just did something that was amateurish, I guess you could say, but I took from here, instead of having this here, I was listening to this circuit and I thought, well, I'm just going to take a variable resistor here, an inductor. I don't even think I use this variable resistor. I may have. There's some internal resistance there. And then I kind of had like two terminals where I would just plug in different values of capacitors. So basically I adjusted this capacitor by hand, just trying different things by hand, and adjusted this up and down. This sort of adjusts the Q, and it's related to the depth, and this sort of does the frequency there. And I just adjusted these by hand until I got something. This was similar. I don't know if these were. I remember this resistor was 680. I don't know the exact values here, but I got something like this. And then the next thing I did was I thought, and what I was doing, I was listening to the circuit, and I'm adjusting all these parameters back and forth until I get kind of a sweet spot where it's really filtering out the nasty portions of the distortion and so forth. And I'm just sort of varying these until I'm really happy with it. Then I took it and I simulated it to kind of look at the curve. And then after that, just real briefly, I built a gyrator circuit to simulate this, and I stuck the gyrator circuit in there. It sounded great. However, I thought, that's a lot of parts for something so simple. So then I took a bridge T, and I did my best to make the bridge T filter approximate what the gyrator circuit or the original circuit were doing. And that's how I came up with this. And by the way, it just so turns out that what I found was it basically was a Marshall tone stack. Now, I don't know if I'm so used to hearing Marshall tone stacks that my brain just kind of adjusted all these things and got me into the same place that Marshall arrived, or if, we both independently just discovered by trial and error that the Marshall tone stack sounds really good. I don't know, but at any rate, this is going to be a similar dip to a Marshall tone stack. And that's how I came up with it, just through trial and error and listening to it. Now, next after that, and this is kind of a bit of a trick that really works well, I think, is that, when you have a distortion circuit, a lot of times you have the distortion, you can EQ it and then re-distort it. And in fact, you can really do a lot with this. And if you think about it, if you have an EQ pedal and some different distortions, you can link low-level gains together, EQ them, especially you distort something, you listen to it, and you're like, this needs a little EQ to make it sound better. Well, you can take it and EQ it, and then go ahead and feed it into another circuit and re-distort it. And this takes care of a lot of, it really smooths things out a lot of times, I think, that whole concept of sort of linking things together and EQing them. It's sort of, we have two gains here. This is basically a sort of an EQ. It's just a mid-range cut EQ. Now here, rather than totally re-amplifying it and clipping it, I just take it and clip it again here. And this is driven pretty hard. It's a soft clipping. This takes care, believe it or not, this really helps smooth things out a lot. I think you could do better even with this circuit if you maybe put some extra stages here and use this as sort of a central brain to the the initial distortion. But this actually helped quite a bit. It just takes a little bit of that buzz out. And that concludes the distortion circuit. Now this here, a lot of times you'll see this too, like I think the Boss DS maybe the tube, I'm not sure if the tube screamer has it, but they just kind of have this little capacitor to kind of take some extra buzz out too. Now, so I ended up putting that there. Now, actually, this I had made, like, for this whole circuit, I made a speaker simulation, and the speaker simulation worked out a lot better with pulling down some of the treble here that was sort of inaudible, but I found that it is slightly audible, and the circuit actually sounds better leaving this in. So I guess you could maybe call this part of the distortion circuit too. So I know this has been maybe a long video for something that should be kind of simple, but really, this is how I came up with it. I took, like I said, the soft clipper, give some good low impedance feedback, drive it hard, EQ it, and reclip it. And this comes out, I think it comes out well. I mean, I probably went through at least, I would say, 50 or 100 designs for sure of just like making a circuit and listening to it. Making it, listening to it, I probably did it 100 times. I mean, this is probably developed over about a year or two, maybe a year and a half, something like that, of just little experiments here, trying to get a sound that's reasonable. And it's kind of hard with a handful of transistors. I mean, tubes say they naturally sound better, so to get something that's okay. I was happy with this. In fact, I built the tube screamer. I like this better, but it's just, I guess it's a matter of taste. But I'll just mention something else. I thought, well, boy, this sounds really good. I'll just make a pedal out of it, right? And I'll just put like a big muff type EQ on it or something like that. And it does not sound like I tried to model a big muff EQ and got it looking right, but there's something. I think it must be phase differences that I'm not taking account in the Bode plot or something else. But I never got this circuit to sound quite as smooth and as good as when you use a tone stack. Or maybe if you use inductors or something, you could get it. But I never really was able to. And you think you could do it, but I've tried several times. And if I were to build this as a pedal, the reason I'm mentioning this, I would use a tone stack with bass, mid, and treble. And you might even, if you really only want a single tone control, you could maybe, if you just want bass and treble or something, maybe just put a fixed resistor somewhere. But I never was able to get it, and I think it probably has something to do with the phase differences that occur in a tone stack rather than like a big muff EQ. But so I guess this concludes this portion of how I built the distortion channel. And if you have any comments or anything, I appreciate them, because honestly I don't run into anyone else who tries to design transistor distortion circuits. That's kind of why I contact people on the internet, because it's kind of this somewhat niche area in today's society. So thanks for watching.